Stephen Adams is an associate research professor at the Virginia Tech National Security Institute. He received a master's in statistics from the University of Virginia in 2010 and a Ph.D. from UVA in systems engineering in December 2015. His research focuses on applications of machine learning and artificial intelligence in real-world systems. He has experience developing and implementing numerous types of machine learning and artificial intelligence algorithms. His research interests include feature selection, machine learning with cost, transfer learning, reinforcement learning, and probabilistic modeling of systems. His research has been applied to several domains including activity recognition, prognostics and health management, psychology, cybersecurity, data trustworthiness, natural language processing, and predictive modeling of destination-given user geo-information data. All right, thanks so much.
Thank you. Good morning. Let's see. Let me get sharing again. I was just trying to pull up the code so that we're ready to go. But while we're starting, I guess how I designed this course was to try to give an overview of a number of different areas of machine learning. So we're going to go very wide and not very deep. So everybody knows that these subjects, I can teach entire classes about a lot of these things, semester-long classes. And so what I'm trying to do is just give an introduction to a number of different areas so that, you're familiar with some terms and some concepts. But I'd like to start with asking, anybody, why did they sign up?
One last
Yes.
Oh, if you can share your screen again.
Yeah, I'm just trying to pull up the code while.
Oh, okay, you got.
Yeah.
Excellent.
And
Thank you, sir.
just trying to get my first notebook up. Well, so yeah, I wanted to start off with just asking why did you decide to take this short course, and what are you looking for from it? So I could try to adjust slides, adjust the tempo of the course. If anybody has any feedback, I'd like to start off with that. No? Yeah.
We've got the Department of Defense to start moving into using more AI and machine learning, so trying to learn more about how the DoD can be implementing machine learning in their acquisition programs.
Great.
How to test it.
Yeah. Test is huge. Our division and institute as a whole is focusing on test of AI pretty widely. I'm not directly involved with a lot of those, but a lot of these concepts will be involved. So it's really important to understand what are some of the key concepts and what are the limitations to this. And so that's what I'm going to try to focus on. So just a quick overview. I'm going to start off with the first lecture today. I guess I got about an hour, starting with just an introduction to the broad field. Then we're going to talk about 3 different types of learning in the next 3 sessions: supervised learning, unsupervised learning, and reinforcement learning. Like I said, each of these is just a very quick overview. We could go very deep into all of these. I'm actually going to put this on slide mode. There we go. And then I'll be demonstrating some of these techniques. Mostly I'll be using Python. I've got a list of packages that I've used in developing these Python notebooks. And I've shared this with everybody. So if you have any questions, if there's anything else I can do, feel free to let me know. Maybe we can discuss during the breaks. So first, what is machine learning? Machine learning is really a subfield of artificial intelligence, where artificial intelligence can be any system that is making decisions based on a computer, whereas machine learning is a specific subfield that learns from data or experience. So one of the kind of examples that I always think about to think about the difference is that, right, a rule-based system, if I just think of a whole bunch of rules, write a whole bunch of if-then statements, that is a form of artificial intelligence, right? Because but that's not machine learning, because the machine learning algorithm didn't learn how to act or didn't learn those rules from anything. Now, later on, we'll see some decision trees that actually learn all those if-then statements from data. So it's very possible. But heuristic type systems are not machine learning. That is the example I usually think about. So as I said, machine learning is divided into generally 3 fields. There's supervised learning, unsupervised learning, and reinforcement learning. A little bit about the difference. Supervised learning is the group of algorithms that's going to try to predict a specific, what we'll call target at this point. So regression is a form of supervised learning. Classification is a form of supervised learning. And what defines it is that we have those labels in our training set. When we're teaching the algorithm how to make decisions, we have examples. So we have some type of input and we have some type of output, and we're going to try to learn. The objective in supervised learning is to learn that mapping from examples. So I'm essentially giving the algorithm the correct answer. I'm trying to teach it. Unsupervised learning is when we don't have that label, that target in our training set. And what we're going to try to learn is strictly from the data. We're going to try to learn characteristics. We're going to try to learn maybe clusters, how to group data without any notion about what the correct answer is. And that's really what makes unsupervised learning particularly difficult, is that we don't have anything about we don't have performance metrics. So if we're thinking about test, you might want to test an unsupervised algorithm that is learning without the labels, but in order to test it, you probably need some notion of the label. And then finally, there's reinforcement learning. And this is probably where a lot of the most advanced AI, machine learning, the stuff that's been making the news, it falls under this RL framework. So I don't know if anybody's a couple years ago saw that computers started to be able to beat Go players, beat the This is all reinforcement learning. And what defines reinforcement learning is that it's a sequential decision process. So instead of trying to learn, how to predict a specific target, how to group data, what we're going to learn is actually a control policy. So how do we act in an environment? And we do this through a sequential process of receiving state information. So basically the state of the world information, and then an agent taking an action and then receiving a reward. And that reward is kind of the main, I would say, teaching instrument, is that you want to try to maximize your reward. And so you see this in this stochastic environment. So those are the three broad areas. So let's think a little bit about applications. Probably one of the most broadly used application, and maybe where some of the most advanced stuff has been in computer vision. So I'm going to give it an image, and it's going to try to identify objects in the image. So here is an example of an image where the algorithm is saying, well, this is a fruit, this is an apple, it's a Granny Smith apple, and I'm also, so there's kind of hierarchy of the different class labels, and it's given a confidence. It's saying, well, we're 99% confident that it's this object. Now, this is a very simple example from static images. There's not very much complexity here. Extensions of this could be video recognition, segmentation, trying to locate, track objects. All of this falls under this kind of computer vision type topic. A couple different traits to this. There's bounding boxes. So this is now the concept of where I've drawn this box around the image. So not only am I identifying that this image contains an apple, but this is where it's located in the image. There can be a lot of complex problems associated with this. One could be, there's multiple objects in this image. How do we look at that? How do we identify where they are? And so what is currently being used for this type of application is deep learning, specifically convolution neural networks. And we can talk a little bit about that later. Now, I do have a quick video, and we'll see how this works. Here we go. So this is a quick clip where we're seeing some different applications of computer vision, where they're tracking these different objects as things are being discarded. right? Overhead imagery. This is a big one for the defense community. Monitoring people. So break-ins, monitoring multiple people. So that's one of the, I would say, broadest applications of computer vision. Now, probably what you've seen the most in the news recently is ChatGPT. Has anybody tried to use this yet? Yeah, everybody. Yeah, so this is under the broad application of natural language processing. Prior to this, a lot of what NLP was doing was trying to identify things in text. So over there, I've got some, just a quick summary of some text about this course, and highlighted some different areas. So that's what for a long time natural language processing was trying to do: identify certain things in text. Another application could be just document identification, classification. So think about like legal settings, reviewing a lot of documents, try to understand which ones are pertinent or not. Email spam was kind of like a classic example of this. But now everything is about these large language models and OpenAI's ChatGPT. This is really exciting because of the seemingly human-like quality to ChatGPT, and the ability for it to do lots of things. I was discussing with somebody over the weekend that they created 50-some job postings using ChatGPT in just a couple of hours, and they said this would have taken us weeks. Talked to other people that said that CPAs are using this now to automatically fill things from financial statements to create documents. So it's incredibly powerful. But thinking about a couple of things, one is security. How secure is this? What happens if I give this data? If I give it documents, where is it going? Another issue is how do we test this? Actually, one of the ways that ChatGPT, why it's so human-like, is because it not only leveraged probably some supervised learning, but also reinforcement learning, and it was tuned with this human-in-the-loop feedback. So it's using models from a number of different fields of machine learning, and it's incredibly powerful. A little scary. But we definitely need to understand how do we test this. Okay, so there's some other things in here, document classification, sentence completion. So you've seen, maybe your email, your text trying to complete things. This could be a model. So actually ChatGPT is a generative model, so it can generate examples. And what is really a lot of under the, I haven't really studied this too much, but what I think is really under the surface are recurrent neural networks. So another form of deep learning. Let's see, I do have another YouTube video, and let's see if I won't be able to get audio, but I think this one's actually subtitled because this has to do with, so. Well, we've already seen some government officials being asked to respond to ChatGPT or to give answers, and then comparing it with a response from ChatGPT. And this is actually one thing that I think that ChatGPT could be really useful for, right? Is looking at requirements documents, looking at bills, creating summaries, doing things like that. But you got to understand that you got to give those bills, those documents to ChatGPT, and then understand where who knows where it's going. It's going to OpenAI someplace. So now so I think a very interesting area of research and maybe engineering is how does the government get a CUI classified version of ChatGPT that it can actually use to analyze different documents. But I think that's incredibly powerful. And again, it's really showing what the power of AI in these models, and we're going to keep refining them over time. So lastly, or I think one of the last another application is games. I'm going to save these videos until maybe we come after the break. I'll try to figure out the audio because there's a lot of audio here. But for a long time, kind of the pinnacle of complexity for games and computers being able to solve them was chess. So for a long time, people were trying, but solve chess mostly using heuristics, kind of these large what I would say is like kind of heuristic if then statement, kind of planning, and eventually we're able to build AI that could beat world champions in chess. The next kind of leap was Go, AlphaGo. Go is a game where you place little stones, and if you think about the complexity, right, the number of possible board combinations, this is much more complex than chess. And about 2015, researchers from DeepMind published kind of a seminal paper in Nature that really goes, that demonstrates that AI, primarily using reinforcement learning, could beat some of the equivalent to grandmasters in Go throughout the world. There's a whole documentary. I think there's like an 1.5-hour documentary that's available. I've got a short clip. Like I said, I'll try to figure it out when we come back from the break. Something I think is a little bit more interesting or a little bit more fun was that DeepMind, after it published this paper, got acquired by Google. And now is basically one of Google's leading RL AI research divisions. A couple years ago, they switched from Go to StarCraft. I don't know if anybody's familiar with StarCraft. I've got an image here. We'll see some of it, but this is a real-time strategy game where humans do something, I don't know, hundreds of clicks or actions per minute. And it's incredibly complex. And so a couple years ago, DeepMind graduated to Alpha Star, which is their AI that plays StarCraft, and put it up against people that make hundreds of thousands of dollars as pro StarCraft players. And we'll see. There's a nice video of that we'll see when we come back. But again, this is now thinking about the state. The number of possible combinations, world states for this, right? It's impossible to enumerate all of them and then decide, well, what is the best action, and to kind of play out every possible sequence. We need some type of AI, when it essentially does this through reinforcement learning. So basically playing games and learning. Reinforcement learning is really based on human psychology, right? That we take an action, we see a response, and we hopefully update our policy to improve that. All of this, all of these AI systems that beat these games were, played millions upon millions of games, observed outcomes, and developed policies. So one of the limitations of this is that you need, and I'll get into the details of reinforcement learning later this afternoon, but you need the ability to play these games over and over again. You need the ability to fail, right? You need to be able to say, well, I took an action. The response is really bad. I lost the game. I don't want to do that again. If we're doing something like training a reinforcement learning agent to fly an F-35, they can't crash the F-35 and then say, okay, well, I learned that was bad. And we can and update our policy to not do that again and keep going. So one of the limitations for this area of machine learning to be really what I would call, applied in a real world sense is that, there are these big barriers to having a reproducible environment, having essentially an infinite data set they can just keep playing games as much as they want, the compute, the ability to do that. So one thing that, a little bit of research that I've thought about is, well, how can we take things from simulations and apply them to a real world? So, maybe we train the agent to fly an F-35 in a simulator where it can crash or do whatever it wants multiple times. And then can we transfer that to like a real system? And how do we then, then the questions become, how do we test that? If we're thinking about testing, do we need to test that the simulator is actually, completely lifelike? Often one of the limitations is that, our area that we're covering in a simulation, right, is, basically what can we think about? How can we design it? It doesn't include everything. So that's one very interesting area of AI that I think is applicable to test. So an area where I've spent a lot of time working is in condition monitoring. So here's, this is just one paper that I wrote, but this is a diagram and a picture of a test stand. This is actually work that we've done for the Navy, Naval Surface Warfare Center out of Philadelphia. And what we want to try to do is predict when these actuators are going to fail. So if you can see from this diagram, there's actually two actuators there. One is like our test, one's simulating the load. You can see it here. And this is just an example of one type of thing. But yeah, our objective is to build machine learning algorithms that can detect the state of these things and understand when it's going to fail. The next step would be, what can we now actually, given our data collected from its current operation, predict how long until it's going to fail? And we can do things with that, like, okay, well, we can maybe plan missions, right? We can decide, well, the ship is coming in to dock. We know that this machine is technically fine right now, but is it going to survive the next 9-month deployment? What's going to be the probability of that? So, yeah.
How many actuators did you actually have to fail to get enough data to train a model to predict that?
Well, so this one, and so this was built by a company, and it's a test stand, and it actually has the ability to simulate faults.
Okay.
So we didn't have to break this, right? That's a big problem, right? And especially in condition monitoring, is that I've been involved with lots of test bed designs for these things. Some that have failed because it's like, well, we're just going to try to wear these things out. You have no idea how long it's going to take. It takes a really long time. But yeah, we designed this specifically so you can see the friction break. So if you can see it from this, right? So it clamps down on the piston, and it can simulate something. There's different valves that we can turn to simulate leaks, and we can simulate the severity of a leak, right? So we can just turn the valve like all the way on. We can turn it halfway on. But what was interesting, and another area that I think is really at the heart of how do we deploy these things, is that we did this study. We're still working on it. We've been doing this for 7-8 years. Year 3 or something like that. We'd actually run this thing enough that it needed its regular preventative maintenance. And we were working with the company, and we took it all apart, performed the maintenance, replaced all the seals, put it back together, started collecting data, and then ran the second data set with our old models. Our old models were 99% accurate. All of a sudden, the models drop, right? They drop in performance. So what happened? Well, we're using vibration sensors to collect this data. Even though we rebuilt this thing to specs, we essentially changed the system, and now we've broken our AI model. Now, there's areas of machine learning. We looked at algorithmic approaches to this. We looked specifically at transfer learning, which is like, well, can we take information from the old system and combine it with, maybe like have a calibration set So that's one approach. We've also thought about the trade-off between, well, we studied these, we collected data through a number of different sensors and found, well, the, vibration sensors are really, really good at predicting the health state, but they're also extremely sensitive to changes in the system. So if we're designing a system, we can establish a trade-off. Like, do we want to trade off a little bit of accuracy for this model to be extremely robust? Or even another system, which is like, well, maybe we actually need to change our maintenance procedures, right? Is have the maintenance tech go in there and, maybe we need a really expensive torque wrench to make sure that this is, all of these things are exactly tightened. Yes. Yeah. And just last thing is that, well, we could also say, well, do we need to start teaching our technicians about the AI algorithm and understanding why they need to do this, and having maybe not a calibration to, is it, we're calibrate the model, but like, let's actually calibrate the responses from the system so that our model isn't breaking. Yeah.
Yeah,
Yeah.
so that's a good point. I mean, this is a lab environment, right? You said it's
Yep.
very vibration sensitive.
Yeah.
So when this goes into operations, it's going to be on a ship that's experiencing all sorts of vibrations.
Yes.
So how do you capture the deltas between your lab environment and the ops environment and build them into your model?
Well, that's what we're trying to do right now.
Okay.
Is like, what happens when we take this? So this is so we picked a commercially available actuator for this. This was an SBIR program. And it was just one that said, well, these actuators are across the Navy. And that's really the challenge. The idea I come up with is that, well, there's probably hundreds of these actuators on ships. There's multiple ships. It has multiple things. And if we're collecting data from all of them at the same time, it really becomes kind of a labeling and documentation, right? Which is that, can we start to understand, we have kind of our lab environment model, right? And then we need to collect some data from all these different operational settings, and we need to use transfer learning or online learning, some type of calibration step when we deploy the models, and then learn from everything kind of in the wild, which is extremely challenging because you need the ability to, well, we're sensing all this stuff, so it's going to go back, all the data is going to go back someplace. But what we'll see from the supervised learning lecture is that the challenge is in the label, right? So I need somebody that, is when there's an anomaly or when they perform maintenance, that's going back and documenting exactly what is going on. Because I've been working in this condition monitoring field for a long time, and I've seen, a lot of variability in maintenance logs and things like that. Actually, maybe maintenance logs would be great to run through ChatGPT to sort and label. But yeah, it's a really challenging problem. Yeah.
Have you tried adding artificial noise to these signals? Something that you have some kind of noise generator that's like what might happen on a ship, and add it to the data you collect in the lab and train on that?
We haven't done that yet. That would be akin to what's like, if you've heard about adversarial learning.
Right.
So how do we essentially try to break these things? We can do different type of sampling methods to increase our data set. No, so mostly what we were doing with this project, so we've done a couple things, is that we first started off, well, I guess one piece of this was that the Navy also came to us and said, we don't want you just to build an algorithm, but we want you to build an algorithm that can go in a box that sits on the actuator and runs on batteries for 10 years.
Right.
And so we can't, I've been talking a lot about deep nets, right? All the reinforcement learning stuff. Those things, you need GPUs, you need a lot of storage, you need a lot of data collection. So that's not going to work. So kind of the first study we did was like a trade-off analysis of a bunch of different algorithms and looking at surrogates for how much power they would consume. Then we went into the feature selection part, which is like, well, if we want to go with a bigger algorithm, we got to pull power and memory on this chip from someplace else. Let's, think about what sensors do we want to put in. We also got to think about the cost, right? So, what is the actual cost of building and fielding these sensors? So we did a lot of research on feature selection. And like I said, then we got into the transfer learning. Actually, right now we're looking at like security. So how do we secure these boxes? I think the next step is then, okay, how do we go from, these lab environments to, a deployed system? How do we look at, there's a lot of different, what I would say, like states or conditions that we can operate this in, right? I mean, this could be the same actuator that is, performing multiple different functions. How does that change everything? So this is, and we're really in a data constrained environment because we can't just continually produce data from the real system. So, most of those examples, ChatGPT is basically using all of the written texts that it can find. And what we've seen is that, AI can do extremely powerful stuff when you give it, basically all of the data. But the question is, what do we do when we can't do that, right? When it's impossible, when collecting all of the data or anything that even approximates that is just going to be, too time consuming, expensive. So, yeah. So this is an area where I've done a lot of stuff. And honestly, I look at a lot of these problems as being very similar. So I've also worked in cybersecurity. I view that as a very similar problem to this. We're trying to detect anomalies. Fraud, done credit card fraud research, kind of the same thing. They all have the same traits. We get a lot of information about the system when it's in good operation. But again, with cybersecurity, with faults, it's limited. We didn't even collect all the possible faults that we could collect here. So we're talking about deployment, right? We've thought about some different architectures. I'll talk about it, I think, a little bit later, which is, how do you, build an out? I think it's all about the stages of the algorithm and the user's understanding, right? So do we start with an algorithm that just detects a fault? So something's wrong with this thing. Then maybe as we learn and collect data, it can maybe start to make decisions about whether or not it's going to tell you what type of fault it thinks it is, what type of severity. But, maybe it can't be for every fault. Sometimes it's just got to say, I don't know what this is. And so I'm a big proponent of having humans in the loop, humans there. Right. So some other things I said I've done, control, I've done some sports analytics. We can, talk about this anytime. Okay. So I've already kind of touched on these things, but some of the limitations, right? Again, data. This is all about data. How do we collect it? How do we label it? This is often one of the biggest problems is how do you label your data? This can be time consuming, expensive. It could require, experts, right? So if we're doing some type of cyber analysis, maybe you need some red teamers in there to tell you what it is. They're really expensive. They've got really important things to do, so they can be hard to get. So you got to store all this stuff. It generally needs a large amount of data. So anything that has to do with deep learning, you need a lot of data. Anything that has to do with reinforcement learning, computation, generalization, right? So we've talked about operationalizing. That's really what we want to estimate is how is this thing going to work when I move from my lab out into the real world. I think one of the things that I see a lot with autonomous driving and other systems is that sometimes, and again, if you're thinking about tests, how a big concern, which is that sometimes the AI might make a decision that a human wouldn't make, and how do you explain that, especially if it's the wrong decisions where it's very obvious that something was incorrect and a human would not have done this. So that's why I'm a big proponent of kind of having some understanding the bounds, what we call the operating envelope of the AI, understanding, having checks built in so it can understand when it's operating outside of its kind of design parameters. It can be confidently wrong. So, I was showing the computer vision stuff and it says, this is an apple, 99% confident. If you all have done a lot of Bayesian work or probabilistic work, that confidence score is it's often interpreted as a probability of being correct, but it's not really learning that. So often what I'll see is that if it misclassifies something, it's going to be extremely confident. So we're doing a lot of work to look at, well, how do we use maybe Bayesian techniques integrated with neural nets to actually have a real confidence score so that, you can assess assess and maybe make decisions about whether or not I'm going to trust this. And then finally, a lot of the most complex stuff is a black box. So if we think about tests, you want to know why it's doing something. The algorithm doesn't tell you. Now, there's a lot of work being done to help, to alleviate that, to try to get insight into how these things work. Because I think a big way to get trust is so if I'm doing, the condition monitoring stuff, I've got a black box algorithm. If I'm showing that, it predicts something because of some particular signal in the vibration signal, and somebody that knows a lot about these systems says, yes, that makes a lot of sense, we're going to gain trust. All right, let me check the time. What do we got until 9? No, 10:15? Is that right? I know. Okay. I think the schedule said 10:15. All right. So what I wanted to talk about, that's kind of an overview. One of the things that I deal a lot with students working at a university, and they all want to jump right into the models and use the most complex models. And a lot of people skip over the exploratory data analysis step. And I think this is like one of the most important things. You've got to understand what's in your data. What does it characterize? Look for things like outliers, look for correlation. Actually, and if you think about, is everybody familiar with Jupyter notebooks? Yeah. So one of my favorite things to do with like new students is to show them about all the steps that I go through with a Jupyter notebook to, load the data, get it into a format I want, do some initial analysis, plot it, and then be like, well, here's the 3 lines of code where I actually built a model and tested it. And that's it. So a couple of things I like to do, obviously plot. So this is some temperature data over time. So I really like to just start all my exploratory data analysis, just plotting everything, understanding, well, most of this stuff is, really aligned, but there's this one temperature sensor that is out, which is different. I think this one's technically outside or something, or maybe in a garage. This is all from a house data. We'll see this data. I've got links to it. So we'll have to start with just plotting the data, understanding what it is. Distributions, I really like histograms. This T1 sensor looks pretty, looks like it follows a Gaussian distribution, which is great. But you got to think about things like, is it multimodal? It does have some other type of distribution. These are things that can affect your modeling approaches. Correlation or pair plots. So this is a pair plot now of all the that temperature data. You can only do this for small. You can't visualize all of this. So I usually like to break them up. So this data set actually contains temperature, relative humidity, all kinds of other things. We'll see it in the notebook. But I like to try to break it up in some ways that I think the sensors should relate, and then plot these because it's a really quick and easy way to understand what's going on in the data, understand if something has no correlation. We get a nice, down the diagonal, we can see that most of these look like they're normally distributed and maybe unimodal. Some of them maybe have multiple modes. Correlation is really important. Again, I like these kind of heat maps of correlation, but if you get up to really large number of features, it can be really hard here. Again, so right now what I'm doing, this data set is, it was really designed to predict appliance energy. So that's why I have the appliance energy consumption in the top row. We can just see very simply if there's any correlation between the temperature sensors and the appliance energy. Other correlation in the data. Then finally outliers. Always a big thing you need to look at, and then maybe a decision, right? So not necessarily just to throw them out, because you need to know something about that. Like, is that a special case? It might make your model work a lot better to get rid of it, but maybe that's the one thing that you actually need to know about, is that outlier. Yeah. Yeah. Well, I generated this artificially, but it's that's a big question, which is what are these? And I always like to understand that, especially when we're doing some type of evaluation, some type of test. I like to understand, well, it keeps getting this one wrong. What is that? What, do we need to design the algorithm differently? What do we need to do to understand and predict that one correctly? And then sometimes you do transformations. So here's the appliance energy data. This is the true distribution over here. You can see it's exponential or something, gamma, log normal. It could be a lot of different things, but if I do a log transform, it moves it to the center a little bit, maybe gives it closer to a Gaussian distribution. Again, I don't know. We just always like Gaussian distributions. Always seems like it works the best when you get a bunch of Gaussian distributed data. Rarely the case though. Yeah, so sometimes you want to transform your data. You can do different types of what I'll call. So usually I talk about input data as being features, but if we want to transform those features into other data, create new features. So these are the things I usually look for when, doing an initial exploratory data analysis. Like I said, it's really important. Try to understand what the data is, and then have that inform your modeling and inform your evaluation of the model. Well, let's switch over to the Jupyter Notebook, because the Jupyter Notebook for this part is centered on exploratory data analysis. So, like I said, this is a data set from the UCI machine learning repository. If you aren't familiar with this, it's got a whole bunch of like classic stats data sets there, like the iris data set is there. There's a bunch of other data sets. I think this is a great resource for pulling, to get open source data sets that's been used for a lot of different things. You find condition monitoring data here. There's fraud data. It's a pretty wide range, but this is what I would consider to be a small IoT data set. So I'll pull it up. All right, so this is the UCI machine learning repository. We can see it's got descriptions of the data, description. This is a pretty good one. I would say the quality of the descriptions and the data can vary. But you see descriptions of the variables. And then often what I like is that maybe there's links to papers. So this is the original paper that this data was published for. Was published in an energy journal, and the objective is to predict the energy consumption of appliances using this data. It's got IoT data collected from temperature and relative humidity from within the house, and also some like weather data from a local airport. And then it's got a kind of a nice feature which has two random variables at the end of this that are just noise, and it's there really. They use this as a benchmarking for their feature selection algorithms to say, well, let's make sure that our algorithms aren't selecting these random variables and stuff, or that there's no impact on the prediction based on this. So it's a pretty good data set. It was collected, listed in a house. I think there's a real family that lived in there. So it's a nice resource. I've also got, I got the link to the paper. So I just ran through a quick exploratory data analysis with this, kind of showing, this is where I generate a lot of those plots. So is everybody familiar with Python and these packages? So things I like, Seaborn and Matplotlib, kind of the standard ones. I always like to just print the data so I can see it. I think it's always just interesting because you got to look at not only just what's in the data, but data types and things like that. So I always start by just trying to print the data frame, seeing what I can look at. Look at some basic descriptions of the data, right? How many features there are, the number of observations in the data set, what are the names of all the different features. All right, then I just created some quick lists to make things a little bit easier. Try to group them, right? So I've got two energy features, appliance and lights. Then I grouped all the temperature and relative humidity together, and then everything from outside, and then the random variables. Is able to produce. Python has this nice describe feature, which gives you the things like mean, standard deviation, pretty easily. Again, just these are just things I like to do at the beginning, just to see if there's anything that stands out. Sometimes you get data and it doesn't change at all, right? You'll see if, so it's pretty easy if you print one of these, if you got zero standard deviation, it's probably not really a worthwhile feature. Maybe you can get rid of it right from the beginning. But there's not too much interesting in here other than, let's see, well, the means are approximately the same except for this T6. I think if you go look at the paper, which has, you know, a description of where all of these sensors are in the house, I think T6 is like in the garage or something. So that makes sense, right? I can see that this is the one I was showing earlier that has a different pattern. Same with relative humidity. We can quickly look at those and the weather. So just being able to print basic descriptive statistics is great. Then I plotted the energy consumption. So there's a couple interesting things here. If we're talking about outliers, we can see that there are these blocks where energy consumption is pretty low. If I remember correctly, when I was doing analysis of this data, this aligned with like weekends. And my hypothesis was this is when maybe the family was out of town. So, you know, the question is, do we want to model that? Do we want to not model that? Yeah, because it's going to definitely throw off your model a little bit. But yeah, starting off with just some general plots. Here's all the temperature data. Again, we saw T6, right, as being probably out in the garage. Here's the relative humidity data, where we can see, again, spikes in RH6. So these are paired, so they're in the same location. I think one of these also was when I was looking at it in the bathroom. So why there's spikes of relative humidity in the bathroom? Probably has to do with showers. So, again, the question is like, is that actually an outlier, or is it something we want to model? Yeah, most of them are pretty consistent. Looking at the weather data, this probably isn't the best one because these are all in different plots. Different time scales, but just wanted to plot things quickly and see. It doesn't look like there's really any significant outliers in any of the weather data. And then applied the random variables, it gets exactly what we'd expect, which is a whole bunch of noise. Then I created a bunch of distributions. So we've already seen the appliance. Lights is interesting because you can see that while the appliance data has a whole lot of, maybe acting more like a continuous value, the number of unique values for the light energy consumption is fixed, maybe even like a categorical variable or an ordinal variable. And then, all of the distributions of everything else. And you can easily print all of this stuff in Python. So I like to do it just to look for, sometimes you can catch, like I said, outliers, weird distributions. Those are things that you might need to consider in the data. So actually right here for RH6, you can see that we get a whole lot of relative, it's very easy to quickly see that this is very different than the other data that we've seen in the data set. And not that we want to necessarily do anything with it, but we need to understand why, right? So that when we're evaluating our model, if we're getting, coefficients that aren't useful, we might need to be making decisions about whether or not to include it. What is the objective of this system eventually? So that's why I like to plot these distributions. It's just to understand what we get. Oh, relative humidity outside has a very different distribution. So we might need to consider that. Then all the external data. Finally, pair plots again. We've seen this one before. Actually, it's interesting that, relative humidity isn't as correlated as temperature. And that, when we get the weather again, just to make it so I could actually see this stuff, because if you throw all 29 features into a pair plot, you can't actually see anything. Can't make anything from it. And then the random variables are actually just copies of each other, which we can see from this. Print some correlation and not much. And that was it. So that's kind of these are the steps that I go through generally with any data set that I get for the first time. And it's always changes. And this is where maybe the students have the struggle the most because they haven't worked with a lot of data before, or if you haven't done, because a lot of this is just, a lot of intuition, a lot of, understanding, well, okay, I see this in the data, I need to keep pulling these threads. But I think that is really a key to all machine learning, which is to not just take your data set and throw it into some model and see what happens. Is that you need to understand what the data is what you have and what it's doing. Yeah, because that's how you get the best models, like I said, especially for test. Okay.
So you said, I forgot which variable it was, but one of them behaved more discreetly, like it was a ordinal variable.
Yeah, the light's energy consumption.
okay.
Yeah.
Right. So is it possible to include that in the same model as the other data? Like how would
Yeah.
so
So some of them have, and this is how, so if you want, I can just treat it as a continuous variable.
right.
If I wanted to make it a categorical variable, or an ordinal variable, and there's, it depends on the model. Some models handle it, so there's only like, I think 7 or 8 unique values. So doesn't have a huge cardinality, but you can, there's a number of different things you can just, some models, most of it comes down to one hot encoding, which is that for each value, I'm just going to set a feature to be 1, and all the other features that are associated with that to be 0. But that significantly increases the, if you think about the, your input size, because now you need n-1 features to describe that. So a lot of times, actually, what I do, and one thing it wasn't in the exploratory data analysis, but sometimes you'll see you have all these categorical variables, and most of them are like, a lot of them will be like one category, and then everything else, could be all these different things that are really small. And what you can do is just say, well, I'm just going to have one feature that says, is it this category or not? And you loop, kind of group it, but this is all now has to do with testing and everything like that. So you can test multiple versions of your model and see how it impacts everything.
Your output space is like a bunch of continuous variables and an integer or something. Like how do you? Sorry.
Well, the output for that model would be it's just a continuous value for the prediction of the energy consumption. Right. So for that data set. I mean, I've actually used this data set for a number of different things, and you can predict all types of different values in this. But yeah, most of it's that's mostly a regression problem. I think I use that in the regression notebook that I have later. We can just see some, and actually the paper does a really great job of describing and performing a lot of statistical analysis of the data. Let's see. So we got about 10 minutes left. Model considerations. So the bias variance trade-off is a key concept to all of this. So error, if we think about it, all models are wrong. They're always going to be wrong. And we can think about errors now being classified into 3 different categories. We have bias, we have variance, and we have irreducible error, right? So variance. So this is a model, like I said, so if we want to predict, this is kind of a classic illustration, but let's say we want our model to be right in the center, right? The true value is right in the center of this bullseye. And so this is a model with maybe high variance, right? So generally it's centered, right? It's kind of predicting, we took the average of all these estimates, is probably very close to the center, but there's a lot of variance. This is one with, so the previous one, this one has no bias, large variance. This is one that has small variance, right? They're all nicely grouped together, but it's shifted off to the right. So there's some bias there. What we actually want is, a model with no bias, minimal variance, but these are often in competition. So as we decrease bias, we might increase variance and stuff like that. A really key concept to machine learning is underfitting versus overfitting. So on the left here, I got an example of underfitting, right? So I've got some data, it's got a curve. The orange line is a model that we could have for this. And we can see it just doesn't really capture anything. It's completely underfit. It's not giving us any real information. So this has a high bias. On the right, we have overfitting, where the model is fit perfectly to our data. However, if I get another data point, and if I get, think about generalization, right? It's going to predict pretty poorly on that, right? So it's going to have a high variance. And so this is something that we're always thinking about in terms of machine learning, especially, underfitting is not really that much of an issue anymore, because I think, but overfitting is definitely something that everybody needs to be conscious of, especially with the large deep learning models. They're really prone to overfitting. There's a lot of strategies for preventing that and evaluating that. But that's, if we're talking about operationalizing, we really need to think about an overfit model. Model complexity, right? I talked about the application of models to condition monitoring. We had a constraint. We needed to fit this thing on a chip. We can't necessarily use a neural net. We have low complexity models like just a simple linear regression model or a tree. And we can have high complexity models like neural nets or ensemble models, which are actually multiple, which can combine a number of different models. Actually, I think with that condition monitoring, I think we ended up using an ensemble, but we were able to control how many models are in there. So, we can always kind of just play with that in the future. But, model complexity, when you're thinking about selecting a model, deploying a model, complexity is an issue. Also, complexity goes hand in hand with interpretability, right? So these linear regression decision trees, they're really easy to interpret. As we get into these more complex models, they become more black box. It's harder to understand what they're doing and why. Sometimes that matters, sometimes it doesn't. Feature selection. So this is, we can go out and collect a whole bunch of data. Not all the data is necessarily relevant to modeling. This is a process I've studied a lot for a number of years, which is understanding what features do we actually want to use in the model and understanding their trade-offs. Like I said, I've already talked about features that are robust to change. Cost is a big thing that I've studied. So as we are building these AI systems, every time we add a sensor, it adds to the cost. We can most feature selection just looks at how much does this sensor improve my model, and if it improves my model, the algorithm says I will add it. But it doesn't account for maybe how much it costs, right? And if I have two sensors that, one has marginal improvement, but is really, marginal improvement and cheap versus significant improvement and expensive, which one do we want to choose? So there are methods. I've worked on a lot of methods to develop techniques for integrating those two things. Okay, so I think that is about it. I just wanted to talk about some resources. So these are some books that I think are great for machine learning. Pattern recognition and machine learning is the two on the left are maybe a little bit old, but they're, I just think it's a great resource. Elements of statistical learning is another great resource. I think a lot of the material, especially in the supervised and unsupervised, I use this as a main reference. And then if you want a newer perspective, this machine learning book by Kevin Murphy really takes it, it says in the title, right, probabilistic perspective. So it's thinking about everything in terms of probabilistic modeling. And I've already mentioned the machine learning repository. There's lots of other, Kaggle is a great resource. There are other specific repositories for data. And I think it's great that, whenever we can put new data sets out there, it just improves the field. So, as you're testing, as you're producing data, the ability to make things publicly available really impacts the field and may improve your ability to assess the data and discover things in it. So I think that is the end of the first lecture. We got about 5 minutes, I think, until the first break. Yes, questions. Great.
I wonder if you could say a few more words about what you mean by irreducible error. So the bias variance is very familiar to me, but I haven't seen it with that code. It's not clear what you mean by it.
It's just anything that can't be captured by bias and variance. So kind of like it doesn't matter how good of a model I'm going to create. There might just be error that is not attributed to anything, or might just be the random nature of the process that we can't capture and model. Yeah.
The bias variance, of course, comes from the expected mean square error. Right?
Mm-hmm.
I was just curious for that. Having a hard time picturing that third term. at all.
Yeah.
Maybe catch us some of it.
Yeah.
I was just gonna say,
Yeah.
do you mind? Our Zoom audience is having a hard time hearing the questions. Do you
Oh,
mind
yeah.
repeating the question as they come in?
Yeah, absolutely.
for them?
Yeah. So the question was, what is this irreducible error term? Again, this is not. My intent wasn't really to be extremely mathematical with this, but just to say that there's, the ability to model something. There could still be error that we can't attribute to any of these. Yeah. So another question? Yes.
Where does the generalization error fit in here, or the generalizability of the model fit in? Is that included in that irreducible error, or where would you include that?
Well, so generalization error. So this is like, so generalization error is usually when we take the error from, what do I want my error to be when I deploy it in an operational environment or kind of on the world state. So I would say that this is, it's a little bit of a different concept, but I would say that this is what we're trying to, I think that the generalization error could be equivalent to the error here.
Yeah, I've
Yeah.
seen it included in the bias variance trade-off before, so I was just wondering what that was.
Oh yeah, like in the
I've seen like a similar equation, but it's like bias variance and generalization error.
okay.
So I was wondering if you're kind of grouping that together, or if you do it as something different.
Yeah, I mean, maybe that's part of the irreducible error. I haven't really thought about that. Usually, I actually don't usually think about machine learning in terms of these characteristics. I'm usually thinking about the generalization error, and I don't usually break it down actually into bias and variance and stuff like that, other than maybe to try to understand whether or not, for statistical measures, right? If I have a statistical measure, something I might want, the something with minimum variance or bias. But a lot of times, what I'm thinking about is just the generalization error and how does it operate in a deployed environment. Other questions?
So when you say generalization error, you just mean the total error for any point that wasn't included in the training data? Or?
I'm usually thinking about it as like, what do I expect? How do I expect my model to perform when I take it out of the lab environment? And that's what we often want to try to. So I think about it, and I'll talk about this under supervised learning, which is that I think about it as, the training data as being a sample, right? It's of the real world. I can estimate some error terms on that. But ultimately what I want to do is understand how is it going to generalize? And so why machine learning like ChatGPT, in my view, is so, seems to work so well when you deploy it is because what they're doing is basically trying to get the training data set to be as close to the population data set as possible. And you don't need to worry about this type of stuff. Right? You just say it works. Yeah. Yeah. Right. So yeah. So, but there could be issues, especially when you get to like specialized concepts. So as you become more specialized, you might want to refine your data and understand exactly what it's being used for. So, right, if I'm using ChatGPT for like specific defense purposes, I probably don't need to train it on Wikipedia because I'm probably adding a whole bunch of error from someplace. Yeah. Okay. Well, great. So, I think we have a break now. I'm going to try to get the audio working so we can watch the StarCraft video when we get back. It's pretty interesting. Great. Thank you all. All right. So I'm going to try to show the StarCraft video. Just to, I don't know. I think this is really interesting. Actually, here, you can see over on the right, the AlphaGo documentary. So if you're interested in this subject, I would highly recommend it. And who you'll see highlighted in this is a researcher named David Silver, who also has a great course on a 10-part series on reinforcement learning that he still taught when he was actually teaching. He doesn't teach or accept grad students anymore, but it's where I based a lot of the reinforcement learning classes that I've taught have been based on his work. And it really goes, like I said, so as I said, I'm just briefly, very superficially touching on a lot of these topics. Reinforcement learning, we're going to spend like an hour on it. I think his series is over 10 hours, probably like 15 hours. And it's really great if you want to, that's a great place to start. And I've also got some resources at the end of that. But we don't have perfect audio, but we'll try to see if this works.
Decades, progress in AI has been measured by how well we've succeeded in playing the games that humans play. We've already created systems that can learn to master chess and Go, and many people view StarCraft as the next grand challenge for the AI community. A couple of months ago, we made an explicit choice to try and scale up and speed up the StarCraft project. The way we went about that was to have different versions of the agent compete against each other on something we call the Alpha Star League. This one learning to beat that one, this one learning to beat that one, and that leads them to improve rapidly over time and discover new strategies.
The way it played, you could see it was getting it. StarCraft has imperfect information and is played in real time. It also requires long-term planning and the ability to choose what action to take from millions and millions of possibilities. Look at that, he looks nervous. We were able to beat Danny, the best DeepMind StarCraft 2 player. That definitely exceeded expectations.
The next step is we're going to book in a pro to play. I think there's nothing better than, big external tests like that to focus the mind.
If they can already beat me, that would be incredible.
I really thought TLO would, beat us.
No matter what happens, just well done. It's been amazing progress, really amazing. Our goal is not just to defeat these players. Our goal is to do it in the right way.
How are you feeling?
Good. I'm a little nervous because
Unlike a human player, AlphaStar can see the whole map at once. But we spoke with TLO and created as level a playing field as is currently possible.
In particular, AlphaStar can't react quicker than a human player can, nor can it execute more actions, clicks per minute, than a human player.
All right, 2 seconds, guys.
I haven't really seen a pro play StarCraft up close. The 800 clicks per minute. I don't understand how anyone can even click 800 times, let alone if doing 800 useful clicks.
after the first match, I knew now it was on, and that I actually have to work pretty hard to beat this thing. I didn't want to lose.
Incredibly, the system held up.
I was surprised how strong the agent was. I actually lost every single of the 5 matches.
Did you enjoy it?
I did enjoy it.
Yeah?
Hey guys.
Yeah.
It's been unfair, all you guys against me. Hopefully I'll get to have a rematch where I get to play my strongest race. Well, then I think I would beat it.
Yeah, TLO is an amazing player, but he plays Zerg, and our Asians play Protoss for now.
With TLO, there was still that but at the end of it, but he's a Zerg player, and so now we've addressed that but.
I guess they need a Protoss specialist, and that's why I'm here. I'm hoping for a 5-0, not to lose any games, but I think the realistic goal would be 4-1 in my favor.
I think he looks more confident than TLO. TLO was quite nervous before. The room was much more tense this time. really didn't know what to expect. He's been playing StarCraft pretty much since he's 5.
I wasn't expecting the AI to be that good. Everything that he did was proper, it was calculated, and it was done well. I thought I'm learning something. Yes! It's much better than I expected it. I would consider myself a good player, right? But I lost every single one of 5 games.
We're way ahead of what I thought we would do, given where we were 2 months ago. Just trying to digest it all, actually, but it's very, very cool. I think that progress has been unprecedented.
It's humbling knowing how many people are working on this project of StarCraft 2. Some of the top minds of the world.
These complexities are important to us because they're representative of something bigger. They're representative of challenges that face the whole of AI, which haven't yet been solved.
I think everybody's just very excited to see what comes out of this, and hopefully that StarCraft is going to be a part of history when it comes to AI.
Yeah. So, what do y'all think about that test and evaluation of AlphaStar? Anybody see any issues? There were some that I thought about when I saw this. It was just about like whether or not it's a fair, apt comparison.
Well, they were only using Protoss. I don't know if that matters that much. But
They pointed that out. Yeah. So they've only trained. So for people that don't know, there are three, not alien or different different groups that you can play with. They all have different skills. They train to one agent. Now they do. This was 2019. They do have agents that they have trained for everything else. Actually, it's pretty funny. You can go find kind of AlphaStar conspiracy videos on YouTube about people claiming that they found it in the wild. Right. So StarCraft, you can go online and you can play other people. And so because we've done some work using StarCraft as a test bed. And so when I was trying to learn how, again, I don't know how to play StarCraft, but I wanted to play it a little bit just to understand like what is this when we're training algorithms? How does it work? So I tried to watch some tutorials and kind of went down a rabbit hole of AlphaStar conspiracy things saying, well, I played AlphaStar and I beat it. And I'll tell you why I think that this player is AlphaStar. But anyways, there's some other things that I thought, or I guess, any other issues with the testing or whether or not it's apt? Yeah.
I don't know if it's just because it's a 5-minute video, but
Yeah.
they said they wanted AlphaStar to beat the player in the right way.
Yeah.
But they didn't say what the wrong way was.
Well, they could make it, they said, a pro player has 800 clicks per minute. A computer could go much faster than that. So they don't want to, they were trying to limit the ability, right, to make you not give it an unfair advantage because it can just perform more actions from quicker. But one thing I think, right, so 800 clicks per minute, I don't know if that's an average or a max, or if there's any variability in that, right? So if I set the computer, right, to do 800 clicks per minute, it's going to do 800 clicks per minute. Whereas a human might have variability and might also, get tired, right? So there's no, they're not factoring that in. I mean, these are pro players, so I don't know if they, so that 800 clicks, I have some issues with that and whether or not that's really an apt comparison. More? Yeah.
Yes. So, different application, but I think the principle remains the same. In the game track mania, there's something called a tool assisted speed racing game, basketball. The issue that comes is that these tool assisted speedruns will start using some seriously inhuman strategies.
Yeah.
They'll just create the craziest bug that flings them right to the finish.
Yeah.
At what point do we say we've reached the limit of what a human can do right and replicably, and we just let the AI run with something completely unexpected to completely change how we play the game?
Right. So it finds a bug in the physics engine of the system. Right.
The same principle applies to StarCraft. At what point
Exactly.
do we say, even with 800 clicks per minute, we're going to use something so ridiculous and
Yeah.
unexpected that just completely breaks how we understand the game?
Yeah, I don't think that StarCraft, but I'll see if I can find another video, and maybe when we come back for the unsupervised learning, we'll show that. It's about hide and seek, and it's all about how if you let these things go for long enough, they'll just find bugs in the code and exploit them. Yeah.
So
Oh,
they were
do we need?
We have a Zoom question.
Okay. Well,
they were throttling the output, the 800 clicks per minute. But in some ways, they've got to throttle the input as well, because a human being, I assume, and I haven't played StarCraft, but I assume that there are multiple data points that you are having to take in, and a computer can take them all in at as fast as they can be updated on the screen. But a human being, you have to move your eyes, and so you may not be. There may be a certain metric that you're only checking on, once a second. So like in that way, it wouldn't be fair. Of course, the computer is going to outperform because they are constantly going to have the perfect information to
and
go off
they
of.
actually mentioned that, I think, is that Alpha Star, it can see the entire entire battlefield, whereas when you start off in StarCraft, there's the fog of war, so you actually only see what's going on locally. So yeah, that's another big advantage for Alpha Star.
So was that Alpha Star aware of the entire map?
Yeah,
all of sorry.
I think so.
Because even if there's no fog of war in this case, you can only be looking at the part of the map that's on your screen, and you're not looking at what's going on over here, right?
So
I assume there's some kind of like alert if you're being invaded from one side or something, but you have to go look over there, right?
Right. Yeah, I think Alpha Star it has full visibility over the map, so that is a big advantage. So what they could do is use computer vision and actually go straight from like screen scrapes, so that the algorithm would need to maybe move the screen around.
It actually has to look at the screen, look at it. Yeah.
You said that there's a
Yes. Are the policies learned by Alpha Star deterministic? So like if they output the same result for each game played?
I don't know specifically, but I would guess it's probabilistic, because usually in games it's better. Kind of a general statement. It's better to be probabilistic because a deterministic policy might overfit to a particular opponent. So yeah, probabilistic policies are usually found to be optimal. One thing that I always, I haven't seen anybody think about this or talk about this in terms of the training time, but I wonder how many lifetimes of StarCraft did Alpha Star get to play in order to achieve that? Is it, if I played StarCraft from the time I was 5 until I was 80, and I played it, this many, 12 hours a day, 6, how many games could I play, right? And how many games did Alpha Star get to play? Because it might be able to absorb and play multiple lifetimes worth of StarCraft, and I wonder if that is a good evaluation or an apt comparison. But when we're thinking about testing stuff, I mean, I still think this is a pretty great example, because you do have a human and you have an expert, and I wonder how much they didn't do much testing generalization outside of this, right? They had their internal players playing, but yeah, generally I think it's pretty good. I'll say, StarCraft is a great test bed for this type of thing. I've seen there are benchmark StarCraft, right? So they're playing the full StarCraft game. There are benchmark simulations that are established for just like combat, and so you can have different, you could have different like force on force, like with heterogeneous or homogeneous agents. And you can train reinforcement learning algorithms to control that. So it has some really interesting techniques or traits, right? Which is like, communication, right? You have homogeneous agents, you have multiple agents. So it's pretty interesting. So in some of the military and DoD stuff, yeah, StarCraft has been useful. Well, great. Any other comments about that? I think that is a pretty good, and also just so you can see, I haven't gone into AlphaFold yet, but what we've seen so far, AlphaGo, Alpha Star, these are playing games, right? Playing StarCraft really doesn't have much impact on the world. DeepMind has, yeah.
Sorry, we do have a follow-up question. If policies are not deterministic, how can a model be learned and applied in real-life scenarios?
How can it be? Well, it's probabilistic in its output, that it's going to take an action with a given probability. And so if you think about something like I've seen a lot of analysis of like poker and different things like that. And, you know, if you're playing against a person, you know, if you're deterministic, you're going to overfit and be predictable. So it's really, you know, probabilistic policies are really, I feel like, crucial for adversarial type scenarios, multi-agent type scenarios. Yeah.
But even in that situation, so
Yep.
sorry, we're here at IDA.
Yep.
The ultimate adversarial situation is things like combat that I think people would still be really hesitant to say, like, oh, it's probabilistic, you know, that we are letting a machine decide actual adversarial with some consequences.
Yeah.
And so what would be the next step that has to be taken to formalize these so that you can do validation and verification on these types of models where the outcome really, really does matter?
Well, I have a lot of thoughts about that. I don't know what I know we're not classified here, but let me think about what. So I think the next level is maybe applying a justification also to a selected action, which is not only why you're taking the action, but some type of, you know, reason why. And I guess I'll say if it's probabilistic, usually what it's going to learn is a policy. It's where there's multiple correct actions, and it's probabilistic because the outcome is stochastic. And so, you know, in reinforcement learning, we are learning, you know, it's a sequential decision problem. So I might want to take a suboptimal action in the near term because I expect, given the stochastic nature of the environment or maybe the adversary, that ultimately I will get to a better state where I can reap a larger reward. But I think that is a pretty big challenge for this. And I guess I'll just say, yeah.
Sorry, just I guess I actually had a comment here. So I mean, like, so you know, you said this is IDA, right? Like, so you know, this is DataWorks. You know, we're all data driven or whatever. But I think this is also where it's important to, like, you know, like something like AlphaStar, AlphaGo. You know, these are neat. But when it comes to what do we want to use AI for? And really, it's to let to aid the human to make a decision. And so, you know, as long as I think, like, where it really, when it really matters, as long as we include a human in the loop, then I think, you know, I think that can kind of help us. Where it's, the AI is not making the decision; it's a decision aid. You know, I think that's kind of an important point here.
Have you all found a lot of success in convincing stakeholders that that's the right option for using AI? That feel like there's a human in the loop?
We can talk offline.
Yeah, I guess I'll try to talk about some general things, and right now just say this is conjecture, but these, you know, if you're going to try to operationalize like a reinforcement learning algorithm for some type of for something like this, you need to make sure that your simulation, right, your game is really very exact to the real world environment, and any deviation from that could cause your model to break and fail. Yeah.
Sorry, I'm getting some stuff in the chat. Can you speak into the mic?
Sure. Oh, yeah. Yeah. Sorry. Right. So these overly complex models don't really seem to generalize very well, is what I'll say. And that what I've seen be more successful, especially in the DoD space, is maybe some simpler models that have some explainability, that maybe don't try to do full control, but actually, right, you have these like decision aid qualities. Yeah, at some point we could talk offline about like specific things that we've seen. Yep. Great. Anything else in the chat before we move on? Nope. Okay. Great. Yeah, so I will, in regards to, I'll find another video. We'll come back at the unsupervised learning and watch a great summary of a paper that basically explored what happens when you keep letting these things run forever and what kind of exploits do they find. But for right now, what we're going to talk about is supervised learning. So this is probably the bulk of the machine learning that is out there, most of the problems. So just starting off with some basics, a little bit of math. What do we want to do in supervised learning? We want to learn a function that maps inputs to outputs. So we have this function. It's parameterized by theta. We have our inputs x. We have our outputs y. The inputs are features. Output is a label or a regression value. And essentially what we're trying to do is learn theta. Theta are the parameters of this function of this model. That is supervised learning in a nutshell. Now, how do we learn? We learn from data, right, when we're doing machine learning. So we have our data set, which for supervised learning consists of X and Y pairs. We assume that it's independent and identically distributed. And what we're going to do is we're going to form some type of loss function. And this loss function is going to provide us a measure of the difference between the true value, y, and y hat, the output of our model. And then we can set up an optimization problem. So what do we want to do? We want to learn values of theta that minimize the sum of the loss over our training set. So again, this is very general. In reality, we're going to pick all types of different functions, all types of different loss functions, different optimization routines. So what is IID? This is an assumption of most algorithms and most statistical models. First off, independent. So it's going to assume that each observation in your data set is independent from each other. Examples of this breaking down was the 2008 financial crisis, where the models didn't account for the fact that, you know, if your neighbor defaults on their mortgage, that you're more likely to default. It assumed that every default was independent. So this is kind of an extreme case of what happens when you don't account for this. In reality, you know, probably most data sets, there's a little bit of dependence in there. Where it becomes a really big concern actually is in reinforcement learning, where we have these sequential models. So actually, whenever you're starting to deal with sequential data, it becomes really important to think about how do you create observations and testing and training set, and making sure that, you know, information in the training set isn't also what I would say present or indicative of what's in the test set. And then identically distributed. So we talked a little bit about normally distributed. So I'm going to assume that my data that I have has the same distribution as the data from the population or in the when I'm going to deploy it in my operational environment. And this is actually something that I've spent a lot of time thinking about, right? Which is that when we're developing test beds, when we're developing test sets, is the data that we're collecting actually follow the same distribution as what we're going to see in the real world, and what happens when that's not the case? Or I'll give you another example was what happens when you know, a system evolves over time, and we build a model, we deploy it, it's working great. In the case of maybe cybersecurity or what I've seen in credit card fraud, the adversaries adapt, right? They start to see, well, my attacks are not working. My fraudulent transactions are not working anymore. I'm going to change my behavior. And then my model breaks because now my data is different. Could be the same thing on the user side. So, you know, maybe interaction with the AI system has changed the user base. Maybe my bank was acquired. And now I have a different customer base, and now all these all the distributions of even the non-fraudulent transactions are different. But so this is something that we think about, we assume, but in practice we kind of violate a lot, or is very difficult to capture. So again, we talked a little bit already about generalization. So what I think about is, right, we have our, the big blue circle is all of the data that could possibly happen. And what we get for our training set is the small circle. But what we want to do is estimate how a model trained on D is going to perform in the population. Again, what most machine learning is doing now is just saying, well, I'm just going to make that D as big as possible. And a couple of things have allowed us to do that. One is that we're collecting data everywhere. I mean, ChatGPT text is all over the internet. Actually, there's APIs just to download everything on Wikipedia. One part is, the ability for us to collect data. Another part is for us to be able to process it. So the the kind of, I would say, realization that GPUs are really good at not just good at graphics. They're called graphics cards, but they actually perform these simple calculations that are often really inherent to deep neural nets. So you can form it incredibly quickly. So we aren't worried about computation as much. Also, computation is, right, every day it seems like we get more of it. We get more ability to store data, right? I mean, a couple years ago, 100 gig hard drive was expensive, and now it's, most high-end laptops come with a graphics card, even if you don't need it. One strategy is, I'm just going to collect all the data as possible. I still think, and where the boundaries start and we don't have answers, is how do we perform some of these advanced machine learning AI algorithms when we are data constrained. So that's generalization. So one basic tool that we're going to use is training and testing. So if we have a data set, we're going to split it into two sets. We're going to train on our training set. We're going to build a model. We're going to have a test set that we withhold, and that's how we're actually going to evaluate it on that. So what does this do? This gives us an idea about one thing. It can indicate whether or not we've overfit our model. I always think of it as if your training error is kind of cheating a little bit, because your model's already seen that data. If it's good, it should be able to replicate it. And so we actually want to test it on data it hasn't seen before. Now, I guess I still often think that, going back to this, is that I'm still just looking at this circle, right? So I'm not really expanding beyond that. And I always really want to know, well, what happens when I start to get outliers? How robust is my model to things it's not even in what we've seen before? Right. So, training and testing splits assume that the data is IID, right? That you're not contaminating your test set with information from the training set. Again, it's also really big in like financial modeling, where you have time series of stuff. So you got to think about how do you create testing and training sets. We've got people that think about this a lot. How do you do this? It's not, mostly what you'll see in classes, and what I'll do is just randomly sample, which is probably not the best strategy, but is what, it's easy, is basically what you can do. So you can, and it seems to work in most cases. But like I said, there's limitations to this. One is that if you're just doing this once, you are randomly sampling. So are you getting the best estimate of your performance? And there's better strategies. I really like cross-validation, but again, there's issues with that. So what is cross-validation? So simply, if this is our data, what we're going to do is we're actually going to divide our data into, in this case, 5 folds. And then we're going to use one of those folds, we're going to withhold for testing, and we're going to train on everything else. And then we're just going to keep moving forward through that, right? And so what we do is, in this case, we'll get 5 performance metrics that we can then use to, now we can, average that. We can look at the variability of it. But what we've done now is, we haven't wasted any data, right? So we've used all of our data set. We've kind of started to understand the variability based on sampling. We can get, what I like is that we can get some type of confidence bound on our estimate. So cross-validation is one of the tools that we'll use. Again, there's a lot of different versions. I'm trying to give like a very superficial overview. There's a lot of nuances to cross-validation. generally, so I just start with some fivefold, tenfold. Again, I always like to, whenever I'm working with a data set, I like to build up complexity of models. So even if I don't think something's going to work, or I think that maybe it's not the best practice, like I want to start with something simple. Like let me do fivefold cross-validation using a linear regression model, and just see kind of what is my baseline, what is my starting point. Okay, so in supervised learning, there's two basic problems. There's classification and regression. So classification is the model is going to predict a discrete set of classes. So we saw computer vision, right? Apple, fruit, right? There's no ordering to that. Most of the time we're assuming a finite set of classes. Really, this is a limitation of the model and something we need to think about, right? So if I have 1,000 different objects that I want my model to recognize, what is it going to do when I presented an object that isn't in that training set, or that isn't in that class set? That is something that needs to be addressed or thought about when we're doing, or in the fault classification, and I'll show you some work on hierarchical classification. What do we do when a fault that we didn't generate from our test stand is present in the in the operational environment? So generally we assume that order doesn't matter, but there's ordinal data. And there are models that specifically look at that. But I'm talking about general classification where, the order of, apple versus banana, right? There's no order to that. And then a lot of times there's binary classification, which is just between two sets. So things like cyber attack detection, something I usually start off with is just thinking about as a binary classification problem, like, is there an attack? Then we can move to a multi-class problem. So not only is there an attack, but what is the attack? What's the type of attack? Same thing with condition monitoring, right? First level binary classification, is there a fault? Multi-class is, well, what type of fault is it? So then there's also regression. So now our model wants to predict continuous value. Again, theoretically, it's all real numbers. I got a star here because I don't know, if you're predicting something like the stock price, it's bounded by 0. I don't know, and there might be other assumptions that you can make, but generally, actually this is something that you got to check your model, right? So theoretically, your model, if you get something that's out of distribution, maybe it predicts a negative stock price, and you can, or there's other examples of that. What I would say is that right now there's a really interesting field called physics-informed machine learning, where we can start to take physical boundaries like that and integrate them in the loss function or some other way to say, like, you're going to get, if you think about the optimization problem, right, that we had earlier, right? So if I predict not only if you're, how far away you are, but if you outside of the physical bounds, we're going to give you a massive penalty for predicting this. So generally, when we think about loss functions for regression problems, right, closer is better. So, loss functions for classification is usually, well, is it this class or not? Loss functions for regression is some type of continuous value. Like, it's better to be close, right? It's better for me just to be a little bit off than to be way off. So some examples, stocks, temperature. So what we've already seen, and so on. Right. So I guess we've already talked about this a little bit. This is the light energy data, right? Is this, we were going to try to predict this. Like, is this a regression or classification problem? Does anybody have an opinion? Yeah. Yeah. So the question, I interpret it as kind of both, or either. Again, all this stuff from my perspective, as I think about operation, is like, what do we want to use this for? Do I want to just predict, like, if something's high, low, like this? Is it better for me to be, do I want to predict in between these values at some point? Does that help? So who knows? Yeah, exactly. You could round it, again, you could have, if you want to get into specifically the models, right, you can predict, right? You can assume, instead of like a regular regression problem that assumes that everything's normally distributed, you can assume it has a Poisson distribution, and you can predict, so you can get really complex. But like the point of this and what I'm trying to say is that, you know, you got to think about these things and understand what you want to do. Again, also, if it's a, you know, if we want to use this as an input, as a feature, we could also think of it as a categorical versus a continuous variable. I think though that like I don't really study this too much, but as you start to get up in the cardinality, right, of this set, it's usually better just to assume that it's a regression problem. This is probably right on the border, but you know, it's something to think about and something that definitely can trip up students where they see. So I have seen data sets like I'm working with some cybersecurity data sets where right, it looks like, or you know, they look like continuous values, but when you like look at the distribution, it's like, well, there's only 2 or 3 real values here. So what are we, you know, how do you want to model this? So again, it goes back to the exploratory data analysis, understanding your data. So measures. So how do we, right, check performance? There's a whole lot of different performance measures. Depending on your problem, you might want to construct you know, custom performance metric that you can actually then also integrate into your loss function. So accuracy for classification is usually one of the basic ones. You know, we can form confusion matrices, which I really like because you can see how things, you know, not only how correct it was, but how is the model predicting when it's incorrect? So sometimes you can look at, well, it makes sense, right, that it confuses these 2 classes. So again, thinking about cybersecurity, some data that is, or a data set I've been working with recently, it confuses 2 classes, but if you look at, like, if you actually go read about the attacks, they are basically have the same objectives or maybe actually derived from each other. So it makes a lot of sense that they have the same kind of signature. ROC curves are also great. Precision, recall, all the standard stuff. There's a lot here. Again, you know, custom performance metrics, like it might be better for me to have, I don't know, false positives as opposed to false negatives, depending on your application, and you can design the loss function actually to account for that stuff. Yeah, for regression, mean squared error, root mean squared error, absolute error, R squared. Honestly, like I usually like to just, you know, it's pretty easy, you know, implementation wise to calculate a bunch of these. And so I like to understand, you know, they each have, I have the ones that I like root mean squared error because I think it's really interpretable. But depending on what you're doing, you might want to look at a lot of these things and often when I don't use a single performance metric, usually when I'm evaluating a model. So I want to look at it over a number of different things. But the main thing here is, to understand, you know, you're trying to basically look at some distance, right? If this is the model, I'm predicting a certain value on that line, and I need to quantify how far away I am. I also like performance metrics that, again, are interpretable. So root mean squared error, if I'm predicting, you know, yes.
Sorry, just a question from the chat. How do you deal with classification performance that varies with time?
Like, well, that I would say that falls into the non-stationary environment type of thing, and something that we've been thinking a lot about. And we call it establishing an operating envelope for an AI system. So if you think about it, I think there's probably a lot of stats people here. You know, control charts basically for AI, where if it's, you know, we expect some type of deviation in performance, but, you know, can we set bounds? I like to think about the bounds being tied to the mission of the system. So when does our you know, if it goes beyond this performance, when can we no longer trust it? When does it actually affect implementation, and trying to set up bounds for that? And then taking that type of a control chart or that type of concept, and then understanding what do I need to do with my algorithm? Do I need to did it go beyond the operating envelope because of a change in the environment? Is this statistical in nature? Is it just we finally hit a sample of our what we're seeing operationally that is different than what we trained on, or did something materially change? And then what do we want to do? And that's where we thought about things like transfer learning, retraining. How often do you want to do that? Thinking about things like, I could theoretically retrain my cyber detection system like every night. Now, is that worth it? Are you overfitting? So on. So it all comes down to operational considerations. So just a quick overview of some different models. Let me check the time. Okay. Right, we have linear models. Generally right now, these are, I would say, usually have the lower end of performance, but I'll say that they are can be pretty robust. So if you're worried about changes in the environment, at least my I would say intuition and what I've seen in practice is that these models, because they're so simple, don't overfit as much and can actually, like when you go out of sample, can perform a lot better than some of the other models that can completely break. But yeah, there's and usually I would say that most versions of models have both a classification and a regression version. So linear models is one. Decision trees are another one that I think are pretty simple, that I really like, in terms of definitely trying to convince people that the system works and that, so when I've had clients, giving somebody a classification tree that's pretty simple. This is stuff I did in sports analytics, where I was working with some golf coaches and stuff like that. We did all this data analysis, and it came down to being we traded off a lot of performance to some basic interpretability and gave them a decision tree. And they're like, we can take this to golfers and we can show them the decision that we've learned, and it makes sense to us and it'll make sense to them. So decision trees are great. What they do is basically divide up. It's a very simple model here on the left. Where we've got just two features, and we're going to try to carve up the space, and then we're going to label that space with some the region like R1 with some type of label, and then what you can do is you'll build a tree, and the trees are pretty simple. So we're going to start up at the top, and we're going to say, all right, if the value of x1 is less than theta 1, we're going to go down the left side of the tree, and if it's greater than, we're going to go down the right, and we keep going down until we hit what's called a leaf node, where then we're going to say, this is the value. R right now is saying that we've entered this region, and we're going to give it a label. We're going to predict based on some label that we've derived from this region. So again, there's classification and regression types. So in classification, what we're trying to do is we want to predict a class when we get to one of those leaf nodes, and or what I usually like to do is more of a probability. So what's the probability of this? So we're trying to calculate the probability of a class being at that leaf node, so we want to learn a model that maximizes the correct probability, and we can use a cross entropy loss function for that. Regression, what we're going to do is actually look at the, when we get into a region, we're going to take the average value of all of the observations that we've seen in our training set. And there's a loss function for that. So in reality, what you do is actually, generally you can grow these trees to be basically have one regression value or one classification value in each node. But does anybody see any issues with that? Yeah. 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 These things are extremely prone to overfitting. So much so that I've seen examples where if you remove one observation, you take your training set, you build a tree, you remove one observation, rebuild the tree, you'll get a completely different tree. And so these things overfit. And also, you're usually to do that, depending on the size of your data set. I've got an example a little bit later where we can see a small data set, but you're getting a pretty big tree. So you're starting to lose a lot of the interpretability of these things. So usually the strategy is actually to build a full tree and then do some type of what we call pruning. So you start to eliminate nodes, eliminate splits. And yes.
The figure on the right is intuitive. How do you describe or think through the figure on the left?
This is how, so on the left, it's how we're carving up the space. So these lines can basically be the different theta. So let's see. So this line, and then are they going to be able to see me if I walk? Zoom? Okay. So this line right here is essentially theta 1 and what we're trying to learn. So this figure on the left is a representation of the 2D space now carved into 6 different regions, and now I can explain it with the tree on the right. So, right, if first node, if it's less than this value, I'm going to go this way, and I'm going to be over in this region, and then the next value of x2 is less than theta 2, so x2 is up there, theta 2 is right here. I'm in region 3. So it's just a visual representation of the tree. And this only works for 2D space. It's just like I said, illustration. So usually what we do is have trees that look like this on the right. And when we're trying to show somebody a tree, I've got Jupyter notebooks are pretty good at displaying them. We'll see that. I would say also this, can also just be written as a bunch of if-then statements, right? So if you think about like deploying this, if you've got it's pretty simple. If you need to write it in some type of like C code or write it to an FPGA, it's pretty easy. So we talked about trees, talked about the ability for them to overfit. Strategies to prevent that. One is bootstrapping. Bootstrapping and bagging. So bootstrapping is the concept of, I have my training set, it has n samples. Bootstrap samples are going to be sampling from the full data set. I'm going to sample n times, but with replacement. So we're going to get some repeated observations, right, in each of these bootstrap samples. And then bagging comes along when we're going to then build a model on each of the bootstrap samples. We're going to take the model output, and then I can average or in some way combine the output of all the different models into a single prediction. So what does this do? This adds some variability, prevents overfitting. Now my what I would say favorite model, the one that I kind of go to the most is the random forest. And again, this is a lot of anecdotal stuff, but I've just seen it. It kind of always, in my opinion, performs towards the high end of models on a wide variety of sets. I mean, of course, every once in a while it doesn't do that well, but in my experience, the random forest is always one of the top models, and it's got a lot of really great features to it that I'll describe. But it's kind of my go-to whenever I'm starting off with a new data set. It's like, all right, let me train a linear regression model because it's really simple, it's really quick. Let me train a tree to see how that does, and let me train a random forest because I think that's going to be like the top end or probably a pretty good approximate of the high end of what we can do in terms of predictive ability. So what does a random forest do? It's going to build a number of trees, right? And we're going to leverage that concept of bagging and bootstrapping. So we're going to sample, right, from our this is a visual representation of our data. We're going to take bootstrap samples of the observations. And what the random forest does that really sets it apart is that then when it builds the tree, it's also going to randomly sample the features. So we're going to build lots of trees, but we're basically building off of, just subsamples of the data. And what does this do? This prevents the overfitting that we saw with we have one tree. So we're going to have a whole forest full of trees. And like I said, so bootstrapping, bagging prevents the overfitting. It's an ensemble method because what we're doing is actually building a whole lot of models. And we can think about a lot of different ways we want to, I would say, accumulate and have a single prediction from the predictions of all the models. Some other traits that I really like about this is that it uses bootstrapping. So we have data. If we go back and look at this, right? So we're sampling right on our bootstrap. We sample and there's out of bag data, right? So there's data that wasn't in our bootstrap sample, and we can use that to then get a performance metric for that tree. And it turns out that actually what we call the out of bag error of a random forest is a pretty good job of approximating the cross-validation error. So when you're using these models, you don't necessarily have to do cross-validation. You can get an approximate for your generalization error strictly from internal metrics. So while you're increasing the training time because you got to train all these trees, you don't need to do all this cross-validation and stuff. The other thing that it does, and all tree-based models do this, is give us some type of measure of feature importance. So if we go back to our model here, if we want to think about how important are features, X1 is at the top of the node, right? It's at the top of the tree. So it would probably be the most important feature, and then so on. And actually, we can build trees where sometimes maybe features aren't even included in the tree. They're completely left out. So, as a form of feature selection. So we can calculate variable importance for a classification tree, but that only has one, essentially sample. But we can also calculate feature importance metric for a random forest, which has to do with how often does a feature show up in a tree in the forest, and how high is it on the tree. And it averages are below that. So we can, while it's very difficult, you can't really, I would say, interpret the individual trees in the forest. There are methods for getting some form of explainability in terms of these feature importance metrics. So those are just traits that I really like. So it has the kind of the nice trade-off of, it has this big ensemble method, has high performance, isn't completely interpretable, but offers some form of interpretation. Then there's neural nets, and this is now what I would bet that when people are, where most of the research is, because these neural networks are have shown to be incredibly important. They're used in regression, classification, computer vision, reinforcement learning, and essentially what we're going to do is we're going to input our data into the nodes, and then through each layer. So each one right here, each of these is a layer, usually called the hidden layer. This is just a standard, called feed-forward neural net. So all we're doing is putting data in, and we're processing through the layers. In the most standard version, what we can do is a linear transformation, where we take the input, for example, which I'll say is HM-1, which is just, let's say, the vector from the prior layer. We're going to do a linear transformation with the weights. We're going to add some type of bias term. So if you look at just that inside the parentheses, that is very similar, just like a linear regression model. Now, where neural nets really get their power is that you then have an activation function, which is represented by G. And this adds some nonlinearity into the model. And then what you do is you just have a whole lot of layers. So it's very simple for a feed-forward neural net. And you can also have this happen, you can expand the number of nodes in each layer. But this is the, I would say, basis for a lot of the machine learning that's done right now. And when you talk about deep learning, that usually indicates having a whole lot of layers. What we do here is we feed forward neural net, put the data in, does these linear transformations, runs it through an activation function. Here I've got a just simple diagram of a rectified linear unit. This is one type of activation function, and simply what it's going to do is say everything below a value z is just going to be 0. Everything above it's going to be its true value. This is how you get some nonlinearity. There's a lot of different activation functions that you can choose from, but we're going to run the data through the neural net. We'll get some prediction y. We can calculate a loss function, and now how this updates the parameters is that what we're going to do is we're going to take the derivative of the loss, and we're going to back propagate that through the network, and we're able to take the derivative with respect to each of the parameters. In this case, the parameters are the weights and the bias term, and then we can update. We can use usually what we use is stochastic gradient descent to update all these parameters. So this is a extreme oversimplification of these networks. There's a lot of math and theory that goes into this. Actually, if you want, I can, a great reference is this deep learning book. So Goodfellow and Bengio were really accredited with pioneering a lot of the work in deep nets. Yeah, that's a very simple one. Does anybody see any issues, or what are maybe the some limitations of this type of model? So one thing is that training is really computationally expensive, right? We're calculating a lot of gradients. It's basically not interpretable at all. Looking at one particular parameter value is at this point not really very beneficial. There is a lot of work on explainability, and actually, what I think are the most interesting explainability methods are the ones that leverage the gradient. So there's and yes.
What if the derivative doesn't converge?
Well, there are sampling techniques. There are so there's stochastic gradient descent, which adds some variability to the optimization process. One thing that you do, there's a lot of, I would say, techniques to limiting the probability of that happening. So usually it's not that it doesn't. Yeah, right. So you have the exploding gradient problem. One thing you need to do when you are using these is that generally it's best practice to standardize or normalize all the inputs so that the gradients don't either vanish or explode. But yeah, that's a concern with these. Right. So I think the main strategy is to make sure you normalize or standardize your data. To keep all those values small so that things don't explode. There are other issues. Overfitting is a really big concern with this. Again, there are strategies to address that. One is dropout. And so what dropout does is you can think about it kind of like as an ensemble method, but during training, what I'm going to do is this is also what's called a fully connected layer, or a fully connected network, where you can see every node is connected to every other node in the next layer. Dropout randomly breaks those connections. So you're building a more robust model. But yeah, that's definitely a big concern for these. Also, you need a lot of data because these things generally are most powerful when there's a lot of layers and a lot of nodes. And so each time, if you think about this, each one of these nodes has two parameters, right? It has a weight and, or I guess maybe just each one has a weight, but then there's also a bias term. So every time you add a layer or a node, you're increasing the number of parameters, which means that I need a lot more data, right, to efficiently tune or to tune these to the correct values. So I was showing a feed-forward neural net. Convolution neural nets are what is usually used for images or video processing. So this is where just a very simple visualization. I'm going to take values. Think about these as all pixels. I'm going to take these pixel values and I'm going to do a calculation on them and try to estimate some type of single value from that, and I can sweep this over the 2D. All I'll say is data, right? So convolution neural nets are usually used for multidimensional data. I can sweep this over this convolution layer, and I can then get kind of an estimate for each region, and I can keep doing that over and over again. So that's the CNNs are like the heart of all image processing computer vision problems. Then there's recurrent layers. So now this has a temporal component. And this is now the heart of most of the natural language processing, right? So if you think about each of these inputs as a word in a sentence, right? What we have now is not only an output, and there's a lot of different formulations for this, but you can see that the hidden layers, so H is like really the hidden layer of the network, is passing information. So I'm not just looking at information at time t, right, to predict my output, but I'm also getting information from the prior value. So this is like a time series version of the model. Again, these are very simple, just so you get some type of introduction into this. What I think is powering ChatGPT are transformers, which are types of recurrent neural nets, but there's lots of different versions of these. And you can combine all these. So you can have convolution layers that feed into recurrent layers that then have like linear outputs. Right, so I've already talked about this deep learning resource. This is the book. There's kind of two main libraries if you're doing deep learning. There's PyTorch and there's TensorFlow. Let's see, one is Google, the other is, I want to say Facebook. I can't remember which is which. Which one? Okay. My personal, yeah, okay. So TensorFlow, I guess, at a very high level, the difference, they both run Keras, which is the underlying package that builds the model, builds the graph that is the model. It has to do with the user interface. So TensorFlow tries to wrap a lot of things into functions. So if you're trying to just get into implementing, you want to implement quickly, TensorFlow might be the way to go because you don't need to do as much coding. In the research setting, I like PyTorch because, even though I have to write out every layer and have to specifically define a lot of the, I would say, workings and training process, I want that capability. I think it's easier to debug. I want to know what's going on in every layer, not just throw kind of a, TensorFlow is more of a black box is what I would say. Okay, so I'm going to switch over to some Jupyter notebooks. Let's see. Yeah. So the first one is, what time does this session end? 11:45? Noon. Okay, great. So what we'll do is just go through a couple of Jupyter notebooks. I got a couple different data sets so you can see some of the functionality of the different models. Are you able to see that? I can make this a little bit bigger. Better? If there's anything you can't see, I'll try to do this. So we're using that regression. So this is just a regression notebook using that energy consumption data set. So I'll skip a lot of the I skipped a lot of the exploratory data analysis. And so really what I'm doing here is actually looking at not just testing and training, but a validation set. What I'm doing is actually pulling out a holdout test set right at the very beginning that I'm not going to use in any of my training. I'm going to take my training set, and I'm going to perform cross-validation so I can start to understand, make decisions about which model I want to use, or maybe the some model parameters, right? So for random forest, one of the parameters might be how many trees do I want to build? So things like that. So what I want to do is segment right away a holdout test set that's not going to inform any decisions I make about my model. I'm going to do all of that here in the cross-validation block, where I'm going to build a model, and then I'm going to take the model, right? So what I usually do is perform cross-validation, do some model selection, what I call hyperparameter tuning, and then make some selections on that, then retrain the model using the model I've selected with those parameters on the entire training set, and then tests on the holdout set. A lot of training in this point. Actually, if you want to get a true, well, let's say true generalization error, you might actually want to run this multiple times. So, like I said, I picked 3 linear models here. Again, I like linear regression models because of their simplicity, the ability to interpret them. Decision trees, again, for simplicity, and then a random forest regression algorithm, because I think that, just in my experience, this is one of the ones that works generally, I would say, the best. Not really supplying any hyperparameters for linear regression or decision trees. I'm telling the random forest that I'm going to build 50 trees right here. Scikit-learn has a nice cross-validation function. So you don't need to build like a for loop, right? One way I could do this is build a for loop where I'm sampling. All of this is built in, where what I can do is provide it the model, which I'm doing right here, the training set, right, broken down into now features and targets, some scoring functions. So right here I'm using root mean squared error and R squared as the scoring metrics, but I can produce lots of these, or I can just add. You can tell it to have multiple scoring metrics, and then I'm giving it, right at this point, I'm just providing K, right, which is now the number of folds in the cross-validation. Tenfold is just kind of like a standard. It seems like it gives enough folds that I can usually produce some type of reliable like variability metric on the scores without going overly without being too computational. I think at some points, I don't know, sometimes I just say, well, 5 is good. You can actually do leave one out cross-validation, which is then on everything, but with the size of the data sets now, that's not really implemented that much anymore. But yeah, I can tell it the number of folds, and I can just run these models. And here, I just got a block that produces is basically taking the outputs of the linear regression model and putting it into a nice data frame, and then printing it. Let me increase this a little bit. So what we've seen on this simple regression data set, where I'm trying to predict, what did I set Y to be? I'm trying to predict the appliance energy. Right. The linear model gives us a root mean squared error of 92, the regression tree 96, and the random forest 72. So again, we want smaller to be better. The random forest seems like it has a better performance metric, and that's also confirmed with the R squared values, where linear regression and regression trees have a pretty low R squared value. Random forest isn't great, but is better. Again, that's one thing to also think about, is that what is a good fit or a bad fit. Some problems are just really hard, and that's like predicting some type of it's a binary problem. Predicting one outcome more than 50% of the time might be really good. If you do that with like sports betting or something like that, you could I think something like 55% would be extremely high. But then there's other problems where computer vision, it's like you got to be 99%. So whether or not this is a good root mean squared error, I think it's worse than what's in the paper. I think they do a lot more hyperparameter tuning in the paper, a lot more feature selection and stuff. Right now, I'm just using the basic, a lot of the basic parameters, but yeah. So it's mostly comparative, is what I would say. Right. So Whether or not this random forest is good is still an open question, but I can say it performs better than the linear regression and the regression trees. Also say I'm just outputting the mean, but we can look at the standard deviation, which I think I have. Right, so here's the standard deviation, and then actually what I did is created some box plots because this is a very simple way to see what is actually statistically different, and this is actually one of the things I've seen in the machine learning field that is really lacking when they're evaluating algorithms, which is that nobody really looks at the variability. They look at simply, well, I got a slightly better accuracy. Now, is it actually better in terms of the variability of the model? That is usually lacking from a lot of machine learning papers that are very highly regarded. Box plots are very, from this plot, it's very easy to see that the random forest pretty much dominates the other two models. And then I took that test set that I removed from the beginning and ran it through the models. And found that it doesn't give a perfect, generalization error, but it's pretty close. At least the conclusions are the same, right? These are performing a little bit worse in terms of root mean squared error, but again, not a big difference between the random forest. So we got some questions here, like, if we're looking at which one based strictly on performance we would select, we obviously predict the random forest, but if we wanted a model that we can interpret, maybe depending on the level of interpretability, we might actually want to choose the linear regression or the regression tree. So the next block of code that I have is, I just took the data and, in the prior example and just, randomly sampled, right, for my testing and training sets. But this is all time series data. So does that make any sense? To build my model on data that's maybe occurred at different time points, and that analysis wasn't really accounting for that. So what I did here is just split based on time. So something like, well, maybe I'm going to say I'm going to take my first month or something. I think I'm taking the first quarter of the data. I'm going to use that to train. I'm going to test on everything else. And actually, if you want to go in and change, it doesn't really change the results very much, but you can change, if you have the access to this, if you want to change, the percentage of data that where we're splitting this, it can be done pretty easily. But what we see, went through the exact same process. So this is now the training error, right? So we can see actually now the regression tree got much better. The random forest got much better. Oh, wait, am I missing? Fit the model. Y test, Actually, in this case, it got better. I think that when I've run this before, maybe changed around the value that the random forest can break. Do I have that in here? No, I don't have that part in here. So I might need to send out some new notebooks. This looks like maybe an older version, or I don't know, I'll have to go and investigate. But the linear regression model is performing pretty poorly on the test set. Where did I pull the test set from? Yeah, So at this split, it's performing much better. If I change the split, I think, let's see if I can do this in real time. Well, we'll come back to that. If this model's, once this model finishes running. What I was trying to demonstrate was that actually it breaks. I think I've got the index way far forward. I think if I go to 50% and then use the first half of the model, it breaks. But and I've seen that happen before with this data set. And mainly what happens is because what we see when we split by time is that this data was collected originally, right, over, I think, from January to like May or something. So what we actually see is that we've changed from, the winter months into the summer months. The data distribution changes. If we split based on time, we're only getting data from the winter months, and when we try to apply it to the summer months, it breaks. But what I've seen happen is that actually all the models perform worse. The linear regression model is actually a little bit more robust than the other models. So, I'll let that run, and maybe we'll come back to that at the end. Move on to classification with decision trees. This is a new data set, again, at the UCI Machine Learning Repository. This one focuses on Parkinson's disease. And I think it's using like audio clips of people with Parkinson's and without, and then trying to take the information in the audio clips and determine whether or not they have Parkinson's disease. So I started off with just a little bit of exploratory data analysis where you can see the distribution. Actually, there's a lot less healthy people than people with Parkinson's in this data set. I did the standard distributions, which I'll skip for right now, a correlation plot. But what I want to get to is that I was able to, one nice feature, right, on this data set, it's not too big, was able to build and print a regression or a classification tree that looks like this. So in here, you can see each of these nodes has information in it. We look at the top here. It's telling you that this feature PPE, if the value is less than 0.134, we're going to go to the left. It tells us the number of samples that we start out with at that node. So there's only 130 samples in this data set, very small. I selected it specifically for this because we're able to print a tree that we can actually look at. And what we can see is that, at the next one, we're going to have 34 that go to the left and 96 that go to the right in the training set. And then what type of which class is most prominent at each of the nodes. If we go down here into the leaf nodes, we can see, like right here, if you get into this leaf node, you're going to be healthy. This leaf node predicts Parkinson's. Only one observation was actually in the training set made it to this node, and 12 here. So that is, and actually on the data set, we get about 90% accuracy. Created a, here, I'm not doing all the cross validation. I think I just did test and training splits just to, so we could see stuff. Created a confusion matrix. And then, the feature importance for the tree. So what we can see is that, right, again, the feature that was at the top of the tree, most important, then cascading down as we go down the tree, and actually maybe even how many times it appears at each node, and that a whole lot of features in the data that didn't appear in the tree have no importance at all. So again, one of the reasons I like these models is because very easy to do feature selection. Actually, and you can use it to find different characteristics of the data. So I've been working with a cybersecurity data set recently. And if you throw a very complex model at it, like a random forest, it's going to build a whole bunch of different trees. If you throw give it to a decision tree, the decision tree actually usually finds that like one feature can completely separate the classes completely, and it builds a very simple tree with one split. So, if you aren't trying these simple models, you might miss that fact. I have students working with this, and they want to build all these deep learning models. And I'm like, well, the decision tree works really well. Now, a tree with one split completely overfits. So, there's trade-offs. But what we can learn is that, the data is actually pretty simple. So then I did some pruning, and you can just see that this is the same data set, same tree. I actually fixed the random seed. So when I'm splitting the testing and training data, but I'm using this, where is it? Yeah, this cost complexity pruning path function right here. which gives us different complexity measures, and we can use that to prune the tree. So this is the same tree with essentially, I don't know if you remember, but let's see, we can go back up, look at this tree, right? It has, these nodes down here, which this tree does not. And if you look at it, you can see, whereas the prior tree that was like fully, let's say, grown, right, had basically perfect classification accuracy, whereas this node right now has both Parkinson's and healthy data in it. So, yeah, and actually you can see that the classification performance, if you just look at accuracy, doesn't change at all. But now if you go look at the confusion matrix, this did actually change. So again, the importance of looking at multiple metrics. You would say, well, the classification is actually exactly the same because our classification accuracy didn't change when we pruned the tree. But we have different misclassifications right here. So let me see if the regression script is finished running yet. Nope, still running. So you can see how long the 10-fold cross-validation is taking with the random forest because it's building multiple trees. Let's go check on one last script where we're looking at ensemble methods for classification. So here I'm using the random forest, but also what I would say is pretty state-of-the-art version of trees in these ensemble methods called gradient-boosted trees. Generally, it's shown to actually have superior performance to random forest, but can take a lot longer because it's got to build sequentially. Uses a concept called boosting that I haven't really explained, but if you go look at that statistical learning book, there's entire chapters on it. So this is a different data set now. This is predicting whether or not somebody will default on their credit card. And what we can see is, so this is also on the UCI machine learning repository. Yeah, larger data set. I think there's 30,000 observations here. Yeah, about 30,000. And what we can see, I'll skip the exploratory data analysis. Again, we see some weird things where, gaps in data. This is always something I want to look at. Right. So one of the first things I did with the random forest is use the out-of-bag error to then sweep over the number of trees. So this is the out-of-bag error rate as I increase the number of trees in the forest. Does anybody have a guess on how many trees we should use in this random forest? This is kind of the hyperparameter tuning part. Yeah, possibly. I ended up using 200 because at the time I don't think I cared about the number of trees. But one reason I like random forest is that generally you can see this trait in the out-of-bag error as you increase the number of trees. Right? So I know that at least, I might get minimal performance if I go up to 500 or 1,000 trees, but it's really starting to level off. So probably not that much of a benefit. Then I did the variable importance. So if you go back and look at it, like this is the pay zero is I think like the amount that's like on your credit card from the prior month or so, or whatever you didn't pay the prior month, which makes a lot of sense that would be the most important thing. It's kind of interesting that age was a big factor that it found, and gender and marriage and education found to not be very important. So that was pretty good if we're thinking about ethical AI and what do we want to use in our model. But yeah, it's mostly actually maybe age might even be problematic if you're trying to implement this. But yeah, most of the values that it finds that are important are based on your payment history. So that is pretty believable, and like I said, it makes a lot of sense that whatever happened the prior month is a pretty good indicator of what you're going to do this month. So I tried also gradient boosted trees. So like I said, this is different. So the random forest can build basically all of the trees in parallel, right? Because all it has to do is sample the data sets, create independent data sets, and I can train each tree in parallel. I could actually spread that across, multiple GPUs, CPUs on a high performance computing cluster. What gradient boosted what boosting does is look at how did my model perform on my data set, and then I'm going to reweight my observations and train another model. So I'm doing everything sequentially. One nice thing that's available in this scikit-learn is that I'm able to tell it to stop if this input right here and this input right here. Since it's sequential, I can tell it to stop. So I'm telling it originally to try up to 500 trees and to hold 20% of the data for validation. But if my performance on my validation set doesn't really change for 5 consecutive iterations, and I'm going to define change as being greater than 0.001, I'm going to stop the process. And what we find is that we get this nice curve where we can see again, this is a different performance measure. It's using deviance, but we can see that it's starting to plateau and that the model actually terminated at 50 some observations, even though it told it could go up to 500. So by changing these values here, you can change the convergence properties. And what we see, did I go over accuracy? Yeah, accuracy about 82 for the random forest, accuracy for the boosted tree, 82. So really no difference, but we can see actually now that the variable importance metrics are a little bit different. Again, pay 0 is completely dominant of this, but the rest are has some different characteristics. So we're right at time for this session. I got a little bit of advanced topics to talk about for supervised learning when we come back after lunch, and I'll also see if we can get the results I was expecting from that other notebook when it finishes running. So thank you all very much.